Imagine a world where everything is the opposite. Up is down, left is right, and matter is antimatter? It sounds like something out of science fiction, but antimatter is very real. It is one of the most fascinating and mysterious substances in the universe. Antimatter is the opposite of normal matter. Every particle of matter has an antiparticle counterpart with the same mass, but opposite charge. When matter and antimatter meet, they annihilate each other in a burst of pure energy. The existence of antimatter was first predicted by physicist Paul Dirac in 1928. He was trying to find a way to combine quantum mechanics with Einstein's theory of special relativity. His equations predicted the existence of a particle with the same mass as an electron, but with a positive charge. This particle, called a positron, was discovered a few years later by Carl Anderson. The discovery of antimatter has profound implications for our understanding of the universe. It suggests that there may be entire galaxies made of antimatter out there, somewhere in the vast expanse of space. In the 1920s, physics was undergoing a revolution. Quantum mechanics, a new theory that described the behavior of matter and energy at the atomic and subatomic levels, was upending classical notions. It was against this backdrop that Paul Dirac, a brilliant young physicist, made his groundbreaking prediction. Dirac was working on a way to merge quantum mechanics with Einstein's theory of special relativity. He developed an equation, now known as the Dirac equation, that described the behavior of electrons moving at close to the speed of light. The equation was a triumph, but it contained a puzzle. The equation had two solutions, one for an electron with positive energy, and another for an electron with negative energy. At first, Dirac dismissed the negative energy solution as a mathematical quirk. However, he soon realized that it could not be ignored. Dirac proposed that these negative energy states were actually filled with an invisible sea of particles. When an electron gained enough energy to jump out of this negative energy sea, it would leave behind a hole. This hole, Dirac realized, would behave like a particle with the same mass as an electron but with a positive charge, an anti-electron. Antimatter is not some exotic substance found only in science fiction. It's a fundamental part of our universe. For every particle of matter, there exists an antiparticle with the same mass but opposite charge. Take, for example, the electron. It has a negative charge and is a fundamental constituent of atoms. Its antimatter counterpart is the positron. The positron has the same mass as the electron but carries a positive charge. Protons, the positively charged particles found in the nucleus of atoms, also have their antimatter counterparts, antiprotons. Antiprotons have the same mass as protons but carry a negative charge. Similarly, neutrons, the neutral particles in the nucleus, have antineutrons. When a particle of matter and its corresponding antiparticle meet, they annihilate each other in a burst of energy. This energy is released in the form of photons, which are particles of light. The annihilation of matter and antimatter is the ultimate demonstration of Einstein's famous equation E+mc2, which states that mass and energy are equivalent and can be converted into one another. The Big Bang Theory is the prevailing cosmological model for the universe. It describes how the universe expanded from a very high density and high temperature state. According to this theory, the universe was a maelstrom of energy in the first moments after the Big Bang. As the universe cooled, this energy began to condense into matter and antimatter. The laws of physics suggest that matter and antimatter should have been created in equal amounts during the Big Bang. This is where a puzzle arises. If matter and antimatter annihilate each other upon contact, and they were created in equal amounts, then the early universe should have been a very short-lived affair. All the newly formed matter and antimatter should have quickly annihilated, leaving behind a universe filled only with energy. However, we observe a universe filled with matter. Galaxies, stars, planets, and even we ourselves are made of matter. The question then becomes, where did all the antimatter go? This asymmetry between matter and antimatter is one of the biggest unsolved mysteries in physics. It suggests that there must be some subtle difference in the laws of physics that govern matter and antimatter, a difference that allowed matter to win out in the early universe. Section 5. The mystery of the missing antimatter. The existence of our universe, filled with matter as we know it, depends on a peculiar imbalance. For some reason, there was slightly more matter than antimatter in the moments after the Big Bang. This tiny excess of matter, estimated to be just one extra particle of matter for every billion pairs of matter and antimatter, is what survived the grand annihilation. This imbalance, known as the matter-antimatter asymmetry, has puzzled physicists for decades. The standard model of particle physics, which describes the fundamental building blocks of matter and the forces that govern them, does not provide a complete explanation for why this asymmetry exists. One possible explanation lies in a phenomenon known as CP violation. CP symmetry, which stands for charge conjugation and parity transformation, states that the laws of physics should be the same if a particle is swapped with its antiparticle, charge conjugation and its spatial coordinates are inverted, parity transformation. However, experiments in the 1960s showed that CP symmetry is violated in the decays of certain particles called kaons. This means that the laws of physics are not perfectly symmetrical when it comes to matter and antimatter. Section 6. Where did all the antimatter go? If antimatter is so rare in the universe, where did it all go? One possibility is that it's still out there, just in far-flung corners of the universe. Perhaps there are entire galaxies made of antimatter. However, there is no observational evidence to support this. When matter and antimatter annihilate, they produce gamma rays. We would expect to see gamma rays from antimatter galaxies. However, astronomers have not observed any such signals. Section 7. Antimatter in our world. While antimatter may seem like a distant concept, it has very real applications in our world today. One of the most well-known applications is in medical imaging. Positron emission tomography or PET scans use radioactive isotopes that emit positrons to create images of the inside of the body. In a PET scan, a small amount of a radioactive tracer is injected into the patient's bloodstream. The tracer travels to the area of interest in the body, where it decays and emits positrons. These positrons then annihilate with electrons in the surrounding tissue, producing pairs of gamma rays that are detected by the scanner. By analyzing the pattern of gamma rays, doctors can create three-dimensional images of organs and tissues, allowing them to diagnose and monitor a wide range of conditions, including cancer, heart disease, and Alzheimer's disease. Antimatter also holds the potential for revolutionary technologies in the future. One of the most exciting possibilities is in space travel. Because matter and antimatter annihilate to release a tremendous amount of energy, antimatter could be used as a highly efficient fuel for spacecraft. Even a small amount of antimatter could, in theory, power a spacecraft to a significant fraction of the speed of light, making interstellar travel a real possibility. Section 8. Unlocking antimatter's secrets. Scientists are working tirelessly to unlock the secrets of antimatter. One of the most important tools in this quest is the Large Hadron Collider at CERN. The LHC is the world's largest and most powerful particle accelerator. It smashes protons together at close to the speed of light, creating conditions similar to those that existed fractions of a second after the Big Bang. By studying the particles that are created in these collisions, scientists hope to learn more about the fundamental nature of matter and antimatter. The LHC has already made groundbreaking discoveries, including the discovery of the Higgs boson, a particle that gives other particles mass. Scientists are now using the LHC to search for new particles and forces that could help explain the matter-antimatter asymmetry. In addition to particle accelerators, scientists are also studying antimatter using other methods. For example, the Alpha Magnetic Spectrometer, or AMS-02, which is attached to the International Space Station, is searching for antimatter particles in cosmic rays. The AMS-02 has already detected a few anti-helium nuclei, which are the antimatter counterparts of helium nuclei. While this is not direct evidence of antimatter stars or galaxies, it does suggest that there may be some interesting antimatter physics happening in the universe. Section 9. The Future of Antimatter. Antimatter, once a theoretical curiosity, is now an active area of research with the potential to revolutionize our understanding of the universe and drive technological advancements. The study of antimatter is intimately linked to some of the biggest questions in physics, such as the origin of the universe, the nature of dark matter and dark energy, and the unification of all fundamental forces. As scientists delve deeper into the mysteries of antimatter, we can expect to gain a more complete picture of the universe and our place in it. Will we one day unlock the full potential of antimatter for energy production or space travel? Will we find evidence of antimatter galaxies challenging our understanding of the cosmos? Only time and continued scientific exploration will tell.